Hello, ladies and gentlemen. My name is Montana Wells.
I'm Joseph Barnes.
And my name is Benjamin Jenkins. And we are Triad Enterprises. Triad Enterprises is a small local firm supplying various services, including but not limited to engineering consultation and small-scale manufacturing. Our mission statement is partnering with others to help them reach their goal. Our client is U.S. Roaster Corp. U.S. Roaster Corp is located in Oklahoma City, Oklahoma, and was founded by Dan Jolliffe. He has served the coffee roasting industry for over 33 years, and he specializes in new roaster fabrication and rebuilding older roasters, as well as coffee grinders. He provides a wide range of coffee roasters, anywhere from 3 ounces to 300 kilograms. Here's a few examples of his award-winning coffee roasters. So our problem statement was to design, build, and test a cocoa bean winnower that meets some specifications. It needs to be affordable for bean-to-bar chocolate producers. It needs to be able to be fabricated at U.S. Roaster Corp facilities. And then it also needs to incorporate competitive features such as unsupervised operation, be easily adjustable, and be quiet and fast. So here's a cross-section of a cocoa nib. In the middle, you'll see the cocoa nib, and it has quite a few fracture marks. This is due to the roasting process, and it becomes quite brittle. And whenever you apply any sort of pressure, it sort of crumbles along those fracture lines. Along the outside is the cocoa hull, and it's the part that needs to be removed. It's thin, brittle, kind of papery, and it needs to be removed because it'll make chocolate rather bitter, and it can also contain mycotoxins, heavy metals, and pesticides. So a winnower is an apparatus that separates the desired portion of a material from the undesired portion. So for our project, we'll start with whole roasted cocoa beans, and then we crush them, and that separates the outer, the chaff part from the nib, and then we separate the hulls from the nibs. So we set a few specifications and goals that we wanted to meet with our project. And so we wanted it to be able to winnow at a rate of 100 pounds per hour. We needed it to operate at an efficiency of greater than 95%. And this means that there's no more than 5% of the nibs in the waste stream. We needed to not allow greater than 2% chaff in the final nib output. That's an industry standard. So greater than 2%, and it will affect the taste of the chocolate bar or whatever chocolate product you're making. The retail price we were shooting for was between $4,000 and $6,000, so we wanted to build it for less than that for a profit margin. And then we wanted to also minimize the moving parts and make it easily cleaned, which are key points for food service products. So the general flow of our project that we followed, we first researched the physical properties of cocoa beans. We felt that if we really understood how cocoa beans worked and what they were made of, then it would help us throughout our project to model more efficiently, so we didn't have to spend so much time in the iteration phase. So then from there we moved on to the cracking method. We designed the cracking method based on the physical properties, and we went through several iterations to try to find the best way. From there we moved on to sorting, and then finally separating the nibs and the chaff. Here's a few winnowers in industry. We started off our project doing quite a bit of research with what's already out there. So on the left, you'll see the Bear winnower type BWI, and it's an industrial size winnower. It can winnow at a rate of 1,100 to 6,600 pounds per hour, which is a lot of beans. The nib content in the chaff is 0.25%, and then the chaff content in the nibs is 1.75. More on our side of things is the right side, the right winnower. It's the Vortex winnower by Brooklyn Cocoa. It winnows at a rate of 88 pounds per hour, and the nib content in the chaff is 0.25, and the chaff content in the nibs is 0.2, and those numbers both come from running the beans through twice. And it retails at a price of $34,000, which puts it out of the reach of many startup chocolatiers. Last fall, we had the opportunity to lead 2 freshman groups. We were tasked with giving them a project that sort of helped them understand the engineering design process. So our first group, we gave them the job to determine a viable air velocity range to separate the chaff from the nib. They utilized the air velocity separator in the Biosystems lab to determine this range. They used the terminal velocity of the chaff to lift it away from the nibs, but still keep the nibs down below. They determined an air velocity of 5.15 meters per second, gave the best sort, but a range of 5 to 6 meters per second was viable. Our second freshman group was tasked with designing a hopper that meets some specifications that we gave them. We told them it must hold 100 pounds of cocoa beans, they must determine an appropriate food grade material, and it must not exceed a loading height of 5 feet. Along with that, they had to make a model in CAD software of their choice of their hopper, and then they also had to contact a material supplier and estimate a price. So last October, we got to visit Izzard Chocolate, which is a chocolatier in Little Rock, Arkansas. They were founded in 2014, and their owner introduced us to the chocolate process as a whole, and he sort of talked to us about his winnower and some of the issues that he had with it and some things that he would like to see better. So here we have a video of his current winnower. He made it himself, and so he uses a food processor to grind the cocoa beans, and this sort of crushes them too far. He makes a lot of dust. He estimates that he loses about 25% of the viable nibs, and when cocoa beans are about $700 for 100 pounds, that's a lot of money if you're losing a quarter of it. So he would like to see a better solution where he has less dust and can keep more of his nibs. He would also like it to be more aesthetically pleasing and to be faster. He said it takes him all day to winnow just 1 batch of cocoa beans, and then having to do that twice a week really takes up time on a process that shouldn't take that long. Last fall we did some testing. Some of the physical properties that we tested, we got some roasted cocoa beans from our client, and we measured 122 of them. We found that the average weight was 1.19 grams, the max being 2 grams and the minimum being 0.5 grams. The average sphericity, which is how close the cocoa bean resembles a perfect sphere, is 0.61, so it's average. And then a max diameter of 28.97 millimeters, and then a minimum diameter of 5.01. And that really shows the variability in physical properties of biological materials. It's very hard to design a system that can handle all of these types of beans. And we have a short video of some more testing we did. We used liquid nitrogen to freeze the beans. So we froze the beans, and then we loaded them into in between the wood blocks, and then we pulled the metal plate, and we were hoping that the liquid nitrogen would freeze the outside, the hull, so whenever the impact would hit it, it would just kind of shatter. Unfortunately, we didn't get those results, and we determined that it wasn't a route that we should take.
So at the end of last semester, we came up with a couple options for cracking the beans. The cracking is a pretty important part because however the beans look after they're cracked sort of determines how you go about separating them. And so one of our designs that we had is this design you see here. It's our high-risk design, and it's an impact design. So we noticed that the beans actually cracked themselves really well and stayed in fairly large pieces when impacted or dropped. And so we came up with this design, which has a paddle wheel that would spin and impact the wheels, impact the beans to sort of crack and keep them in larger pieces. This design would have been really simple to manufacture and build, but there's a lot of dynamic elements involved that we would have to test to ensure that the beans would get cracked consistently across all of their different varieties. And so we came up with another option, which is much more common. It's a roller design. It's almost an industry standard. It's really robust. The output of the beans is very consistent. It's well known. And given our time constraints and the amount of testing that would be required for our impact design, we opted to go with a roller design. And so, moving on, once we decided we were going to go with roller, we found this roller mill in our department's annex, cleaned it all off, and installed a variable drive on it. And we were able to use this machine to test various roller gaps, various roller speeds, and multiple passes on the beans to simulate if there was a stacked roller design. There's a video watching it sort of give you an idea of how it works. You can see the rollers there, and that's down in the hopper. Surely ate some beans. So after we would roll the beans, we would want to get some numbers on how well the beans were cracked. So we utilized a machine called a rototap, and essentially you stack the sieves up, and it helps separate the beans based on their particle size. And so we came up with a range of sieves that were useful for us, and after every roll test we did, we would rototap the beans and evaluate how well the crack came out. Here's a short video demonstrating how the rototap operates. So it's pretty coarse, but it makes pretty simple sense there. And it just beats it until they fall through. So here's some of our data. These graphs here are comparing both a 7mm roller gap and a 9mm roller gap. And within each graph, you have a high speed and a low speed roller process. As you can see in the 9mm roller gap on the right, you have very little dust, and the dust is what we would consider waste because you can't sort it. However, you see a whole lot of material that got caught in the first sieve. And that's because there were whole beans that didn't get crushed, and so if you have a whole bean, you can't really separate it. But you can also notice in 7mm you have a much nicer spread of material throughout all the sieve stages, but you also do have much more dust. Also notice that the slower speeds, the orange columns, did mitigate some of the dust production in the 7mm roller distance. This graph shows various roller gaps at a single speed. So here we have a 7mm, an 8mm, and a 9mm roller gap. Again, we can see that the 9mm roller gap had very little dust waste, but again we have a large amount of large particles at the very first sieve, which was due to beans not being cracked. You can see that 8mm was our threshold that we found for getting all the beans to be fully cracked and to start seeing a more uniform spread across all of our sieve sizes. And then 7mm also helped mitigate some of the dust and waste production. Further testing, we tested a double pass. So on the graph to our left, we have a double pass at 12mm and then the second pass at 10mm. And we compared that with a 10mm and an 8mm double pass. And the idea of doing the double pass at such wide gaps was that the beans may have been compromised on the first pass, and through the second pass they would have actually been cracked and would have been able to winnow. And also 2 passes we were hoping to mitigate some of the dust waste production. Again, we can see at the 12 and 10mm double pass that there was still a fairly considerable amount of beans that had been uncrushed in our top sieve, again explaining the low dust or waste production. But we can also see that the 10 and 8mm had a fairly good spread and was more successful than the larger gaps. When we compared a double roller of a 10mm and then passing an 8mm with a single pass at an 8mm roller gap, we see that we mitigated some of the dust production against a single roller, but we decided that given our time constraints and our budget, we would go ahead and pursue a single roller design, but we did see evidence that multiple rollers does help mitigate the dust or waste production. Here we have a model of our prototype. It is a fairly robust design. It's got rollers, it's got an easily removable hopper, it's got a fairly small shop floor plan, floor space. It's fairly easy to operate. There's 2 switches, and then the operator just puts in the beans, and it can process beans at a very high capacity. What makes this model up is starting with our rollers and our housing. So we have half-inch steel plate housing, which houses 2 12-inch long by 7-inch diameter rollers that have been grooved to help feed the beans in. Those are supported by food-grade pillow blocks, bearings with 1-inch shafts, powered by Schedule 40 chain, and we featured a pivot roller in there to adjust the gap using linkages and a threaded nut so that within our range you can infinitely adjust the gap. Moving on beyond that, to drive our rollers, so to spec out our motor, we took our roller mill that we had access to test with, and we loaded up the rollers full of beans as worst case scenario, and then pulled up on it to see how much torque was going to be required to power through fully clogged rollers. We then decided how much torque that required per inch of roller, scaled it up to our 12-inch rollers, and we came up with a number of around or greater than 600 inch-pounds of torque would be required. Taking that to the marketplace, we were able to find this Dayton gear motor, and this gear motor is a 1 horsepower motor with 605 inch-pounds of torque at 85 RPM, and it was going to be well up to the task. We double-checked to make sure that that motor would be well enough. Used our horsepower equation, and the horsepower equation said that it needed to spin at 105 RPM, and this was going to be spinning less than that, so it was going to be perfect for our application. To power this motor, because it's a 3-phase 220-volt motor, we had to use a variable frequency drive, and we went with an ABB ACS 310 variable frequency drive. It features the ability to input a single-phase 220-volt and output 3-phase 220-volt to the motor to make it more accessible to more wall outlets. It features a ton of built-in programmable options as far as startup rate, starting torque, dwell times, and things like that. More features than we've had time to test with, but it's a very capable and good product for what we're trying to get done. Moving on, we had initially planned on having a TROM, which is a rotating drum, and we would have 3 different stages of sieve sizes spec'd out here, which would help separate the beans. And by sorting the beans to their various particle sizes, we would be able to fine-tune the velocity that would be required to separate the nibs from the chaff. But given our time constraints and how simple the design would be, we just sort of left that out and moved on. That would have been housed in the frame that we actually did build for our prototype, which is a very simple design, 1 1/4 by 1 1/4 square tubing throughout. It would be a simple fabrication, quick and easy, very good for low-cost production. Moving on to the separation, we utilized a shop vac with 170 cubic feet per minute of airflow. What else do we have? We have a cyclone separator to help separate the dust out to keep it from clogging up the vacuum. We used PVC pipes for our routing, and we have 2 discriminator valves involved to fine-tune the amount of suction force that the beans see as they're processing through to help sort the chaff from the nib and improve efficiency that bean to bark producer may see. What was required in producing this prototype was obviously assembly, but there was a lot of lessons learned in how you tolerance and call out threads and things like that. So we ran into some issues, but it's important to test fit everything. So all the way to the right we see a test mock-up with the roller body just tacked together. So we went ahead and mocked everything up before we had everything fully welded. Here we have the PVC getting test fit before it was glued. So it's important to go through and make sure that everything will match up before you set everything up irreversibly. So here we have the test fit of our roller and roller bodies with our bearings. And here we found a lot of issues that we needed to address before moving on with fitment, tolerancing, and things like that. One of the things you could note here is that the shaft on the motor goes out to the wrong side. We knew that going into it, but when we reviewed the parts diagrams of the motor, we found that it is offered that you could swap the shaft. And so we went ahead and purchased that, and having to swap the shaft was part of the assembly process for us. And then here we have our finalized prototype with all the pieces put together.
So we also did some finalized testing on our prototype, and we start off with the actual cracking portion, of course. So with the cracking portion, after testing the rollers into the VFD, we found that the best frequency to actually crack the beans was at 30 hertz. And basically what this means is that 30 hertz is the frequency that the rollers will, the input frequency, excuse me. At this frequency, we found that we had consistent cracking all throughout, and the beans were continually just being able to go through and be fed through. We did notice, however, that at lower frequencies, we had a jamming issue within our rollers. The beans would actually clog up the rollers and prevent them from actually going through and feeding through like that. If overloaded, again, the rollers would just jam. Another issue that we found was that the spring tension on the adjustment feature was insufficient to keep the rollers in place. The actual force of the beam being cracked and pushed through was pushing the two rollers apart. And that was making a negative impact on the consistency of our cracking, because some beans were able to get through if they were pushed through, if the rollers were not actually jammed. With the winnower, we were able to find that the air velocity going through it was capable of pulling out almost all of the beans, even whole beans. So we knew that even if any crushed bean that we actually be able, it would be within our range to actually winnow out. But we did notice that large volumes of cocoa beans greatly reduced the amount of efficiency that we had with winnowing. Basically, our system just got overloaded with too much in the air. There wasn't enough air pulling up through it to actually winnow it properly. And we would get too much chaff within our nibs, and it wasn't at all sort. We do believe, though, that the trommel sorting process would greatly help this issue, because not only would it separate the nibs and chaff into precise ranges of particle sizes, which then can be used to adjust the separation proportion to specific particle sizes, but also alleviates the total amount of volume that one individual sorter, air separator, has to deal with. We did also notice that we had to actually manually feed the winnower to keep it at the rate that was required, because just dumping in, we weren't able to do it at a slow enough speed for it to feed properly. And so we would actually just have to manually dump in the beans. This kind of negated our goal of actually being able to just leave it there alone and have it run, like turn it on, walk away, you're fine. Currently, with the prototype as is, you have to manually do it, which is something that we would like to address. We have a video right here. So as you can see right now, I am tapping in the beans through our winnower, and I'm trying to keep it at a constant rate just to basically make sure it doesn't jam. And we basically went here, we did this over a period of a minute, and we're trying to get close, because the amount of cocoa beans we had in there would be equivalent to 1.6 pounds, which 100 pounds of cocoa beans, you divide it by 60, that's 1.6 pounds a minute, which is why we were kind of going for that sample size. At this actual sample size, we were able to figure out that should the feed rate be kept constant around this rate, we were able to get actual efficiencies that we were looking for as far as the winnowing and actually as far as waste and nib loss. So testing results of actually, once we were able to not only calibrate the sorting component of our winnower and do the manual feed rate in, we were able to actually reach the feed rate of 1.6 pounds per minute, which will be scaled up to 100 pounds per hour, which we were really happy about. We found the window efficiency, a lot of times we got up to 98%. So right here, as far as you can see in the waste portion, we have the nib portion right here. This is this is what we want to keep. This is what you're going to make the chocolate out of. And this waste portion is basically throwaway. It's the chaff, it's the very fine dust particles that you can't salvage within the nibs. And from this, we were able to find very little actual salvageable or usable nibs. So that was a very good indication. And this chaff right here, this chaff was actually picked out of the total nibs, as you can see right there, our product stream, indicating that while there was still chaff within it, there was still a very small proportion. And from a lot of the samples we were getting around 1 to 1.7% chaff within the window cocoa, which is very good. It's still below the 2% range. And actually, if we can address the feed rate issue, would be very competitive. Moving on to the financial breakdown of the Winworm, our overall budget for this prototype was $3,000. And once all said and done, the material cost of the project ended up being almost $2,000. With the cost of control systems, the VFD being around $300. We did not include labor costs simply because through the labor donations of Mr. Dahl, and also utilizing the Biosystems Machinery Lab and the technicians there, they all were able to help us fabricate the entire process, and so that came to no charge to us, which we were very fortunate of. Another thing that we were able to do, we got a direct donation from the Gilroy Manufacturing. They actually donated the cylinders, the steel cylinders that we used to make our rollers. And that was valued at $348. And so that was actually a big help on us, and that did not go to our cost for the prototype. So at the end of the day, our prototype cost ended up being around $2,000, which was well below our budget range. The final design, financial breakdown. Our target production cost was from $3,000 to $4,000, so that way we can hopefully turn a profit after like selling at like probably $6,000 or $4,000. After you take into the cost of the cracker, the trommel separation mechanism, and also the trommel sorting, and then the separation part, the material cost for the actual product would be about $3,500, which was significantly more than what our prototype cost was going to be. The control costs, what we would estimate would be $576, and then labor was calculated. We basically took the average fabrication technician hourly wage of $20, multiply that by 3 for 3 workers working, and then an 80 hours for 2 40-hour work weeks. We believe that we kind of believe like this would be a very good conservative estimate to figure out how much labor would actually be able to put into that. And labor, as you can see, is a significant portion of the final cost of the our final estimated cost was $8,285, which is out of our target range. And so in that aspect, we did not quite make that. Moving on to perhaps some ways of improvement, we developed this tool called the Failure Modes Effects Analysis. And of this, we basically input different things where we see failures within our prototype and within our final design. And from there, we assign values based on severity, rate of occurrence, and then the level of controls that we have in place. And we assign a value to that, and from there, we calculate what would be our main parts. As you can see, our top 3 were operator safety, roller movement during cracking, and then also food contamination or food safety. Those are the 3 areas that we really feel like we do need to address and focus in on any more iterations of this design. So with our recommendations, the first one is operation safety. Right off the bat, we need to add a chain guard. We weren't able, on the cracker assembly, it was powered by the motor, which turned the chain to turn the gears. Right now, there is not an actual guard around that, and so that is open to air, and it is possible for someone to come up and stick their hand in it and get caught and lose a finger. That is very bad, and we've actually on a prototype had to tape off the back area of the Winworm just to make sure that no one tries to go over there while it's in operation. So that's just the first one. Unfortunately, we weren't able to address that quick enough within this prototype. The next one is add emergency shut-off controls when areas of moving parts are accessed. So let's say the guard for the chains is taken off, or someone tries to get in or around the rollers while it's rolling. we would like to initiate an emergency shut-off where the entire system shuts down to prevent anyone from getting hurt in that aspect. On subsequent iterations, we would like to make the window shorter overall. It's a little over 5 feet right now, and so even someone my height, it would be hard for me to fully load it to capacity. So not only is that kind of dangerous, it's kind of it's not very ergonomic on any person, but also making it shorter would make the maintenance overall easier and cleaning of the product easier. And finally, we would like to reduce the entire weight of the machine. Right now, it's a very heavy machine. You cannot just lift it up and move it wherever you want. And so that really kind of makes it hard. And also add, of course, more warning labels overall throughout the design. So on the roll and movement, what we're planning on doing would be what we would do was to increase the spring tension and add a spring guide to decrease or eliminate roll and movement. Basically, we want to make the shoe stronger. That way, when the beans do go through the rollers, it's less likely that they'll be able to be pushed back and not crack in that aspect. Finally, on food contamination, we would really like to upgrade all the materials to food grade materials. While that would actually increase the materials cost for design, we think that in the long run, it would be not only a better selling point, but also would make design just overall more safe and in some cases even more efficient. And so a couple of materials that we may suggest would be, of course, stainless steel or EU, H, and V, W, excuse me. The last part is to make all components easier to disassemble. Right now, even with our prototype, all the piping for the separation component, they're all PVC, they're glued together, you can't take them apart. So that indicates that there may be many chances for particles to accumulate within the piping, and that would be very hard to get into reach, and that's a food safety concern. And so that really needs to be addressed, and also other issues throughout the, even like with the rollers, making sure we get in there, get them complete properly. So that really does need to be taken into consideration in further iterations. So comparing our goals and specifications. So with the winnowing rate, we were theoretically able to reach the 100 pounds per hour, but that is with manual feeding on that aspect of it. So while our winnower can reach that rate, you do have to, of course, be there all the time, which defeats the purpose of having it automatically. We were actually able to either get the efficiency of 95%, and in some cases, some of our testings, we even got a little bit better on that aspect, so we were very happy on that. Typically, we got very little nib loss within our waste stream. On the 2% chaff in the product stream, some of our samples, when we calibrated really well, we got up to 1%, and then some of them, when the calibration maybe got out or perhaps our feed rate got messed up, it would be like 1.7. Regardless, we never ever got a chaff percentage by weight more than 2% throughout any of our samples that we were able to take. For the production costs of $3,000, $4,000, we were not able to meet that goal. There may be ways actually to reduce the production costs because a lot of the materials that we bought were wholesale, like we bought them straight from the store. And so there may be ways around that. And also, depending on what materials you make or decide to use in the future, could also bring that down. Ease and clean, that still needs to be improved overall. There's still a few key points that would cause some food safety concerns and that need to be addressed. And finally, moving parts. Really, the only moving parts that we have on this design is the cracker. Everything else is either gravity fed or suction. And so in that aspect, we really felt like we did a good job. Overall lessons learned, we had organization, communication, prioritization. Ooh, basically, these are just general things that we felt like that we learned during our year design. With organization, we felt like we kind of learned how important it is to really focus and divide the workload and figure out whose role is what and how you're going to go about doing that. With communication, it is very vital that everyone on your team knows exactly what's going on, how you're going to do that, and just who you need to talk to get it done. Not only between us, faculty, even our client, just how important communication is. And then finally, prioritization. With that one, just knowing not to get too caught up on one specific aspect of the design and letting a few perhaps fall on the wayside, just being able to have a good grasp on everything and what you need to do to get it done. So with that, do we have any questions?
Give this group a round of applause.
Between the roasting and cracking, does it matter what that length of time is or what the storage of the beans are between the end of the roasting process and the?
That would be kind of up to the actual owner of the facility. It is probably suggested that once you immediately roast it, you then crack it. So a lot of like the facility that we went to, the man who was making the chocolate, he wanted to basically roast the beans, then crack them, winnow them, sort them out, and then immediately start making chocolate, because if you do leave the bean, like even the nibs out for longer, there is a chance that they could, get contaminated. And that's
So he was putting warm beans into his
Yes.
cracker?
Yeah, his beans, yeah, for the most part. He would let them cool to a certain extent, but then transfer them over to the warm one.
Did you guys ever look into textured rollers, more of like a mill roller, or are all the rollers for the beans smooth?
Our rollers actually aren't smooth. They have grooves cut into them. So, yes. We did try with smooth rollers as well in the lab, and yeah, it didn't work very well. It didn't grab onto them, so we did add grooves to the rollers, and it does help grab the beans and force them through. Yes, sir.
I'll start off easy and I'll come back. But anyway, how many lines per inch were you running the roller cut? I didn't see that when we came in the shop. How many lines per inch were you cutting across the roller?
I don't remember. It was
Okay. You do green cuts or all longitudinal cuts?
all longitudinal.
All longitudinal. Not good.
It was the largest tooth cutter you guys had.
Do you think that the depth of the cuts or the amount of cuts per inch make a difference in the product?
I think as long as there are grooves, it'll help mitigate any sliding of the beans. At some point, you're balancing. At some point, you'll start to grab the beans, and then at some point, you're going to make the rollers hold on to the cracked beans and make it a little more difficult to clean them and have more bean buildup. So the smoothness, the teeth per inch, and the depth, you're starting to get into sanitation, cleaning, maintenance, cleaning schedules and things like that. But for the most part, as long as there's some texture, it'll grip the beans. But the fear would be having to clean them more often and how much the beans stick to the rollers themselves.
If being sticking to the roller is a problem, the roller maybe have a wipe on it or something?
Yeah, we weren't able to incorporate a wiper. We had planned to, but that would definitely help keep the beans to sort of self-clean themselves off the rollers.
I would like to have your comments on the size cuts you think would work good on the report. Do you think it would have been better served with a longitudinal cut and a ring together, or should you do the two longitudinal like together?
We didn't get to test with any kind of spiral cut mill rollers, so we don't really know what effects that would have. And at this point, the teeth on the rollers haven't really been the limiting factor. They grip well enough to bog down the motor, so that's not really what's limiting us at this point. We have a lot of the right elements. I think the elements we have just may not be well balanced with each other.
I
So,
think you did an measurement with dig into the kind of information. I'm gonna stop the message or the question, and I'll come back.
Question, sir?
Is both of your rollers run at the same RPM?
yes, sir.
Okay, in the wheat industry, we make flour, one roller runs faster than the other one. And that strips the bran off of the layer of wheat. And I was curious if you would run one roll faster than the other one, it would roll that bean.
Yeah, we were exposed to very non-matched speed rollers when we were investigating some of the coffee bean grinders that we sort of were inspired by on our roller design, but we never had the opportunity to test various speeds. We could have probably bought some different pulleys for our test roller mill, but we didn't actually test any of the various speeds, so that's a whole other avenue that may increase or decrease the dust production on the roller mill. So
How do coffee beans differ from cocoa beans?
Coffee beans are a lot harder
Yeah.
overall. Cocoa beans are a lot softer, and also they have a lot higher fat content. So when you do crush them, we always have the issue of actually maybe getting some of that fat out and collecting on the rollers, collecting throughout the system. You know, from as I understand it, we don't see that as much with coffee beans. But that's probably the main differences that I would suggest.
Why did you use a three-phase motor? Could you have used a single phase and then reduce the cost of your controller as well?
that was sort of driven by the torque requirements that we tested with. So we had already cut our rollers, and then when we determined how much torque it used on our test roller mill, we had to scale that up for the rollers we had made. And so had we found a single phase with that much torque, I'm sure we would have gone with it, but we weren't able to find one, so we had to go with a three-phase motor.
Any other questions?
I didn't quite, on your prototype that you built in the lab, I didn't quite pick up on what you were using for a separator there. What did you finally do on your prototype to separate?
We go back to that one.
So we used a shop vac, and that provided our section. So the shop vac is connected to the Cyclone with the reddish black hose. It's in the back. The Cyclone sucks the chaff out and it spins it down into the waste bucket, the black bucket, so that it doesn't go into the vacuum and clog up the air filter. And then we used PVC. It's in front of the machine, and so the nib or the beans that are crushed fall down, and then due to the vacuum, the chaff goes up and the nibs fall down. And so we have two.
So point with your finger on your finger. I'm lost in your plumbing.
Okay, so here's the inlet to the PVC.
Okay.
I'm going to the slide. I think there's a
Okay, there might be
better
another.
angle.
Go to the front.
Yeah, I had that separation. Go.
So we put the beans in the hopper, and then our roller housing is in here. So it rolls down through and gets crushed. Then we have a funnel that the crushed nibs and the hulls go through. We have a PVC tubing attached there. So then it falls down through there, and then we have it drops here, and that's where the nibs go. And then the chaff goes up. And so we have a valve here and a valve down here. And those are discriminator valves, so we can open and shut them to control the airspeed. For our final design, when we would have a trommel in this area, we would have three basically, so that we could separate based on the size. So the larger sizes, obviously the chaff needs a bit of a higher air velocity, and then as you go down in size, the chaff requires less. So that would just increase our efficiencies. And so the chaff gets sucked in through there, it spins around in the Cyclone and falls down in there.
Okay, so here's my follow-up question.
Okay.
Your data appeared that you were doing a very good job of separation. And so why wouldn't you stick with a similar, why are you trying to improve your separation when you've already surpassed your goals for separation when a very simple device seems to be doing the job?
Mostly because it would make it more marketable. Some of the other winnowers that we found, they had very high efficiencies, well over 99%.
like 0.2, 3.
And so our client Dan, he seemed to want a very high efficiency. He thought that would be a good selling point, especially if it was at a lower price than some of the other winnowers that are over $30,000. Another suggestion that we did have that's in our report is to have various models. So maybe we could have a lower model that's a bit cheaper like this, and then have upper models maybe with dual stage rollers and a trommel or some other system.
Does that answer your question?
Yes, very good, thank you.
Okay, let's give this group a round of applause.